Section 8.5 are going to be looking at trapezoids and kites. These are our last new quadrilateral types that we're going to be looking at. And today focusing on trapezoids. Now a trapezoid definition is a quadrilateral, of course, it's four-sided, but it's a quadrilateral with one pair of parallel sides, and those parallel sides are called your bases. As you notice here, these would be my parallel pair of sides. So, but only one pair of parallel sides. These are called your bases. So those parallel sides called our bases, and we also have two pairs of base angles. And we kind of associate the angles that are off of the same base as being a pair. So there's a pair of base angles because it's off of this base here. But we would have another pair of base angles, these two angles then off of this bottom base. So trapezoid, one pair of parallel sides being opposite, two pairs of base angles, and the non-parallel sides are actually called your legs. Kind of like in an isosceles triangle, in a sense. Now, think about a trapezoid. You have this one pair of parallel sides. These legs do not have to be congruent, and most likely are not. If they are, you have what's called an isosceles trapezoid. Now, remember how an isosceles triangle had two congruent sides? Well, an isosceles trapezoid has two congruent sides as well. It's the legs that are congruent. So first of all, if it's a trapezoid, you have this one pair of parallel opposite sides called your bases and congruent legs. This is what makes it isosceles. You have those two congruent legs. Also, remember how isosceles triangles had two congruent sides and two congruent base angles? Well, each pair of base angles is congruent then in an isosceles trapezoid, which is kind of neat. So think like isosceles triangles, you do have base angles congruent. So here, these two base angles are congruent, both acute, and these two base angles are congruent. These are both obtuse. Now actually, you only need one angle measure in an isosceles trapezoid, and you can find all of them because we know that these two angles would have to be supplementary because they're off of parallel lines. These are like consecutive interior angles, so those would have to add to 180. And then these are congruent, and these are congruent, the base angle pairs. And also these would have to be supplementary or add to 180, which is kind of neat. Isosceles trapezoid, you'd only need one angle, and you could find them all. With a regular trapezoid, yes, the base angles off of each base are supplementary, like these two would still need to add to 180 because they're off parallel lines. And over here, these two angles would still need to add to 180, but again, they're not congruent, so you would need one of these two angles and one of these two angles to be able to have all of them. And another cool property of isosceles trapezoids. A trapezoid is isosceles if and only if its diagonals are congruent. So if I draw in the diagonals here, these diagonals themselves are congruent, and I could mark two tick marks representing the entire diagonal is congruent to this entire diagonal. Now this only happens in an isosceles trapezoid that the diagonals would be congruent, and it works both ways. If you have congruent diagonals, then it is an isosceles trapezoid. Keep in mind, on a regular trapezoid, one diagonal here, this would be much longer than the other diagonal here. So that only happens in isosceles trapezoid. Let's look at some examples here. The top of a table is an isosceles trapezoid. Find the missing angle measures. This is going off of what I was just talking about, that you only need one angle measure in an isosceles trapezoid. First of all, if it is isosceles, I could do a lot of things here. Isosceles trapezoid means these legs are congruent. Of course, if it's a trapezoid, you have one pair of opposite parallel sides called your bases here, so these would be parallel. But yeah, I can find all the missing angle measures because I know that the base angles are congruent. So these two base angles are the same measure, making this 65 degrees. And then I know that the angles between the parallel lines here, these consecutive interiors, would have to add to 180. So I'm doing 180 minus 165 and getting 115 here, which would have to be the same angle measure because the base angles are congruent in that isosceles trapezoid, or again, these two would have to add to 180 as well. So one angle measure in an isosceles trapezoid is enough to find all of them. All right. I notice I do have a trapezoid here because of the fact that these two sides are parallel. Looks like we have the diagonals drawn in. Let's see here. If EG equals FH, is trapezoid EFGH isosceles? What are EG and FH? EG is this diagonal, and that's congruent to FH, which is the other diagonal. Hey, remember what we just said? A trapezoid is isosceles if and only if its diagonals are congruent, which means it works the other way as well. If and only if tells you it works both ways, that if diagonals are congruent, which is what I have right here, then the trapezoid is isosceles. Congruent, so yes, trapezoid EFGH is isosceles. Okay, because of the congruent diagonals. Okay, some more here. If measure of angle HEF is 70 degrees, where is that angle HEF? So that would be this entire angle being 70 degrees. And the measure of angle FGH is 110 degrees. FGH, vertex at G. Okay, I'm going to have to do two arcs. There's a different angle, but it's talking about that whole angle is 110 degrees. Is a trapezoid isosceles? Okay, I'm pretending I don't know this part here. We said it was isosceles because of this. Starting over, let's say this is all I knew. And now I would not know these diagonals were congruent, okay? But I have these angles. Does that mean the trapezoid's isosceles? Well, remember, you have an isosceles trapezoid. I'm gonna go back a little bit. If the base angles are congruent, and actually, I don't know if I read this one, but if a trapezoid has even one pair of congruent base angles, it is an isosceles trapezoid. So that's what I'm trying to see here. Do we have a pair of congruent base angles? Well, taking a look at the fact that this is 70 degrees. Now, the thing I do know for certain, these two have to add to 180, be supplementary, because they're off of the parallel bases here, and they're consecutive interiors. So now what would add with 70 to give you 180? This would have to be 110. That I know for certain. Hey, look, now I do have a base angle pair congruent. It is isosceles. By the same token over here, these two angles, no matter what, have to add to 180 because of the parallel lines and their consecutive interiors, right? Same side of that transversal in between the parallel lines. So this would have to be 70. Again, base angle pair is congruent, so yes, this trapezoid is isosceles because the base angle pairs are congruent. And technically, I only needed one to show that it was isosceles. So looking at two important properties that make a trapezoid isosceles, if the diagonals are congruent, as we saw in the first example, oops, I have to mark this one, and if the base angles are congruent, as we saw in this second part. Oh, and then we're talking about mid-segments of trapezoids. So this is a cool extra segment we're going to talk about here. A mid-segment of a trapezoid is a segment that connects to the midpoints of the legs. Get it? Mid-segment connects to the midpoints of the legs in this case. So I need to find the midpoints of the legs. Well, these are the legs, right? So let's say the midpoint of this leg looks to be about here. Does that look pretty good? That would prove it's a midpoint. I gotta find the midpoint of this leg, which I'd say was about there. And it's a midpoint if those two parts are congruent, if it divides it in half. So the mid-segment itself is this red line I'm putting in right now. One of my points must be just a little bit off here. Because two things happen with mid-segments. First of all, a mid-segment is parallel to each base. So remember how the bases have to be parallel in a trapezoid? Well, it's also parallel to those, so I could have all three of these marked with that one arrow. And the length of the mid-segment is half the sum of the lengths of the bases. In other words, it's the average of the two bases. Which means if you know that this base length was, say, 8, and I knew that this base length was 12, the mid-segment would be the average of those two. Now you know how to find the average, right? You add, divide by 2. So I would do 8 plus 12 and divide that by 2. I'm trying to find the number between 8 and 12, and you can probably just see this. Or just know, because 8 and 12 is 20 divided by 2. And is 10 in between 8 and 12? Yes, it is. 10 is the average, 8 and 12. It's the length of that mid-segment. The trickier example comes when, let's say I know the mid-segment and one base. So let's say that I know that this is 25 and this base is 36, how about? And now I'm looking for this base length here. Now I could do the algebra and say, well, I know that the mid-segment is the average of these two bases. So if I added the two bases, which are x and 36, right? X and 36 are the two bases. If I added divided by 2, I would get the mid-segment, which here is 25. So I could set this up and do the algebra, multiply by 2 first to cancel this out. So x plus 36 would equal 25 times 2 is 50. And then I could subtract that 36 and get 14. Okay, cool. So I figured out that x is 14. I want to show you an even better way, or an easier way to do this. Remember how right away we did an example where it was 8, 10, 12? You know that 10 is the average of 8 and 12 because the difference between 10 and 12 is 2, and the difference between 8 and 10 is 2. So if the difference between both is the same, you know you have an average. The reason I'm bringing that up here is you can do the same. If you're looking for a base, you can say, well, I have the mid-segment in one base, and what's the difference between 25 and 36? If you subtract those, that difference is 11. So the difference here should be 11 as well. So you do 25 minus 11, hey look, you get 14 that same way. So I guess there's kind of a shortcut or an easier way to do that, thinking about what we know about averages. So talking about mid-segments of a trapezoid, it connects the midpoints of the legs, it is parallel to the bases, and then its length is the average of the bases. Let's do some examples using mid-segments here. First of all, this is a trapezoid because I noticed the bases are marked parallel. I know that HK is a mid-segment because H must be the midpoint of GD. I see these congruent tick marks. And K has to be the midpoint of EF because I see the tick marks again. What variables am I looking for? I guess I have to find HK and ML, and we'll find this variable Y. So let's start out with HK. Alright, HK is the mid-segment, so its length should be the average of the bases. The bases are 8 and 18. To find the average of 8 and 18, I know I add them and divide by 2. 8 plus 18, I'm looking at 26. Divided by 2, it looks like HK is 13. And let's check that here. If this was 13, what's the difference between 8 and 13? It's 5. What's the difference between 13 and 8? Also 5, so that looks good. What about ML? Where is it? Oh, we're going to find that down here. My bad. We'll do that next. And then I have to find this variable y in this problem as well. Well, the only other degree I'm even given is this 45-degree angle here. Now, there's something we know about these two angles. Seeing that this mid-segment is also parallel to the bases, these are consecutive interiors, right? They're on the same side of this transversal. They're between the parallel lines. So I know these should be supplementary or add to 180. So really I'm thinking 180 minus 45 would be angle Y. That would have to be 135 degrees. The other way to think about that, 45 degrees, this would be a corresponding angle with 45 degrees, so that's congruent. And then these two would also have to be supplementary because they're a linear pair and they have to add up to 180. So either way you think about that, Y would be 135 degrees, knowing the mid-segment's parallel to the bases. And then it's down here that we're supposed to find ML. Okay, ML is this base. It is a trapezoid. I see the parallel markings here. By the way, this is a mid-segment because this must be the midpoint of this side, proved by the congruent tick marks here, and this is a midpoint of this side, JM, proved by the congruent tick marks. Remember, a mid-segment's parallel to those bases. But also, if I look at the length of this mid-segment, being 17, it should be the average of the two bases. If I call ML, I guess I shouldn't call it X because there's an X right here, I'll call it Z. Then 17 would have been the average of 23 and Z. Now I can do the algebra, or we can just use that kind of shortcut in a sense, and realize that if 17 is the average of 23 and z, then the distance, or the difference, I should say, between them should be the same. So what's the difference between 23 and 17? Difference would be 6, right? They're 6 apart. So then 17 is 6 away from this base length. I did 23 minus 6 to get 17, and then 17 minus 6 would give me 11 for that base, or ML. And if you check that, is 17 the average of 23 and 11? Well, you would add 23 and 11, get 34, divide by 2, and yes, you get your 17. And then what about angle X in this picture? Again, because a mid-segment is parallel to the bases, we have these angle pairs that form, and actually in this case, I know this 110 degree angle here, and angle X is a corresponding angle with 110 degrees, and corresponding angles need to be congruent. So X should be 110 degrees as well, and you can tell they're both obtuse angles there. They're corresponding angles. They are congruent. So today, talking about trapezoids and their properties, isosceles trapezoids and their extra properties, and then mid-segments of trapezoids.